In this video, we'll go through a precise description of what we mean by a topology, and we will use this to describe these things called topologies on the real line and in general on Rn. This will allow us to define precisely what we mean by a topological space, and that in turn precisely describes what we mean by a shape. And what we will find is that once we describe what a topological space is, the definition is actually a lot looser than you might think. It's not actually strictly a geometric figure like we've been drawing. So it will allow us to extend the definition of a topological space to more abstract mathematical objects. So to preface this, I want to say that a topological space is just a set endowed with a special something called a topology. So once you put those two things together, you get yourself a topological space. Another similar example where we did something like this is when we defined a group. Now, a group is just a set with an operation. It also has to contain identity, inverses, and all that stuff. But the observation I want to make here is that the common ingredient in both of these abstract definitions is the notion of a set. So this should already give you an idea of how important sets are to mathematics. Without them, we wouldn't be able to define the central objects in many important areas of study. A topology now is just going to be a way of classifying certain subsets of my big set X. In particular, we want to be able to describe certain of these sets as open, in the same way how we have in R an open interval. Okay? Now, the rules for a topology are as follows. Firstly, I require that my empty set and the whole space itself, X, are open. So I'll put it in quotation marks here because we haven't actually described what the word open means. It's not actually something that you can describe. It's just that once you define the topology, that tells you exactly which things are open and which things are not open. The second rule is that the topology is closed under any kind of union you can imagine. In particular, let's say you have a family of sets, AI. These are just a bunch of sets inside my X, and let's say that I know in advance that they are all open. Then the big union is open as well, and I want to remind you that this lambda over here, it just is an indexing set, and it's to take into account that possibly we may have infinitely many of these AI. So when we do the big union, we have to also union across all these infinitely many AI as well. The other rule for intersection is going to apply, but only in the finite case. Now, this might be a little bit weird, but it actually turns out to be very important as a condition for our topological theory. So if we have n subsets, and we know that they are all open, then so is their intersection. And here I've given you indices from 1 to n. So you can really interpret this thing as A1 intersect A2 intersect A3 and so on, AN. Okay, that's a bit of a tricky definition. It's very abstract. There's nothing really that references any of the geometry that we are familiar with. And so that's why we have to describe the topology usually in something in terms of a basis. Okay, so in general, the topology on a set tends to be too big, and so we would like to describe it using a sort of subset of the topology, but with that subset, we would like to be able to derive every single open set again. The parallel that I can think of to draw here is with art. In art, you have these primary colors, blue, yellow, and red, and when you mix them together in varying amounts, you can form basically any color. In a similar way, with topology, we want to have a basis, which is a sort of subset of the topology that is easier to understand and work with. But the point is that when we mix the basis elements together in a nice, neat way, we will be able to derive every open set. In other words, we'll be able to recover our entire topology again. So what is a basis? It's another tricky definition. Here we have a bunch of symbols, but let me just explain in English what the symbols mean. It says that every point inside my space is contained inside a basis element. So in other words, let's say I have my set X, pick an element in X. Well, I need to have a basis element that sort of contains X. The other rule for a basis is that for any two basis elements, if I have some element inside their intersection, then there is a third basis element inside the intersection that also contains X. That's a lot of words and it's a little tricky, so let me draw a picture. So here we have B1 and B2 like I've drawn. here's a point x inside their intersection. And what I claim is that if my collection of b's is actually a basis, then there better be a third one contained entirely inside the intersection that also contains x. So really think about this statement here and make sure you understand why the symbols translate directly to the English that I've written over here. All right, so what I explained was a topology, and then I explained what a basis was, but I haven't told you how the basis actually generates back the whole topology, like how the primary colors generate every single color. So here's how. For any space X, we will call a subset U open if every point is contained inside a basis element that in turn is contained entirely inside U. That's also a very tricky definition, but a picture really helps in this case. So in other words, I have a subset of my set X, U, and I want to determine whether or not it's open or not. So what I'll do is that I'll draw out my set U, I'll pick any point inside it. Now, my space is a basis, is an open set if I can find a basis element, Bi, that contains x0, and in turn it is contained entirely in U. Now, it's very difficult to draw this because it may not be clear why my chosen basis here, which I actually haven't drawn at all, is going to work. But maybe if I specify some basis elements, then it'll be a little bit more clear. So here, let me specify a few basis elements. I'll draw this one. I'll draw this one over here, right? And now I won't be able to get all of them, but I can get some of them, right? So let's say I just give you a couple of basis elements, and just to speed up the process here, I'll give you another one that just does all this, right? So now we see that the condition right here is satisfied because every point inside U is going to lie inside some basis element, and that basis element will in turn lie entirely inside U. Now, what I haven't drawn here is the other basis elements that we need, because remember, for a basis, we need every point to be contained in some sort of basis element, and it also has to satisfy this intersection rule, and that's a little tricky. So in general, a basis will typically be infinite. It will be impossible to draw, and we'll have to rely on some other neater description of the basis than literally listing out every single basis element. Okay? But in some cases, this is possible, and in case you're feeling a little lost by the amount of definitions and the amount of abstractness going on, I'm here to reassure you that the previous two definitions will, for the most part, not be brought up again. There are, however, 3 examples of a topology and a basis which are crucial to what we are doing in this program, which is why we have to talk about it. We will cover 2 today and 1 in a future lecture. The first one is the standard topology on the real numbers. Here we have a basis that is the set of open intervals. Now you have to think about why exactly is this a basis. Well, we can call them open, and they are exactly the open intervals that you are familiar with. But the reason why they are considered a basis is precisely because open intervals, the set of open intervals in R, satisfies these 2 rules. For any point, you can imagine that there is an open interval that contains the point. And if I have 2 open intervals that intersect, well, there's another open interval that lies inside their intersection. So schematically, what this looks like is I have a point X here, and X is contained in the intersection of 2 basis elements, right? This is B1, here's B2, because remember, a basis element in R is just an entire open interval. Well, what my rule for a basis tells me is that if this collection, the collection of open intervals, is really a basis, well, there better be another open interval contained inside the intersection that also contains X. And sure enough, that's not too hard to draw, at least in this picture. Okay, so let's see here what our topology actually includes. Of course, by definition, we have to have all of R, and we have to have the empty set. Any basis element is in the topology. And also any collection of open intervals, because remember, a topology, you're allowed to union together anything you want, as many things as you want, as long as you know that everything that you're unioning together is already open. So any collection of open intervals is fine, and as long as you intersect finitely many open intervals, then you're fine as well. Okay? Here's an example of something that is not open in R. Remember that in one exercise, I described a collection of nested open intervals. They start at -1 to 1, and then they went to -1/2 to 1/2, and then -1/4, or -1/3, I think, to 1/3. And they just kept on going down and down and down and down. If I were to take the intersection of all of these, actually the only point in the intersection is the point 0, right? Now, what our rules here describe is that the point 0 is not an open set. So in other words, 0 is not an open set. Okay? And this aligns a little bit with our intuition. An open set in Rn is just basically any collection of open intervals, because it turns out that the union of open intervals is either just an open interval in itself, or it's just a collection of disjoint separated open intervals like this. Okay? But that one, the singular point 0, is not an open interval. And in a similar way, any sort of singleton set is not going to be an open interval as well. All right. So here's how we would test for openness in R. Remember, the basis generates the topology, and I described how the basis generates the topology. We need to make sure that every point inside my subset, my candidate subset U, has an open set that is contained entirely in U. And this has to be a basis element. Okay? So now that we know that our basis is the collection of open intervals, the question then just becomes, can I construct an open interval containing some point x, and that open interval, can it stay entirely inside U? If the answer is yes, then we're good and U is open. And we can say that it is inside our topology. Otherwise, U is not open, and it does not belong inside our topology. So here's an illustrative example that shows you why basically every single open interval is still an open set inside R. So here I have a half-closed set. It is the half-closed interval from 0 to 1. Let's pick any x between 0 and 1 first. So that means we're not going to think about the point 0. If I pick any such point, well, you can think of a way to create basically an open interval that lies entirely inside this half-closed thing. And the way to do that is really to just take the distance between 0 and 1, see which one is smaller, and then once you have that, well, there you go. That's your open interval's radius. So there. That one works, okay? Actually, for any point between 0 and 1, you could just as well take the entire open interval 0, 1, and that would be fine as well, right? That's an open interval, and it also lies entirely inside the half-closed interval. So this is totally fine. And it looks like our openness test is working for these few points. However, now we pick the point 0. So this is fine. So now we pick x equals 0, and now we notice that there is a problem. What is the problem? Well, if I pick my set 0, I need to try to create an open interval that lies entirely inside this half-closed thing, and it has to also contain the point 0. But notice that no matter how I create my open interval, like this or like this, right, there's no way for me to get this entire open interval to squeeze inside the half-closed interval. And this is the problem that makes this set, the half-closed interval 0, 1, not open. Right? And the reason is that every open interval that contains 0 will contain points less than 0. And those points will not be inside our half-closed interval. So in that way, we have actually shown that this set here is not open just because of that single point 0. Okay. Now, the reason why we're going through this abstract definition is because the topology is the most basic property of the topological space, and actually all the other intuitive properties that we know, like things like homeomorphisms or continuity of a function, or things like connectivity or boundary, all of those things are described entirely in terms of the topology. And that's a little abstract, and it is actually what is done in an undergraduate topology course. We won't do most of that today. But the last thing we have to do today is describe the topology not just on R, but on Rn. And for that, I want to remind you what the unit n ball looks like. So remember, that's just the set of points that are distance less than or equal to 1 away from 0. Here I drew the 1 ball, the 2 ball, and the 3 ball. And I want to highlight here that when we ignore the boundary, we call it an open unit ball. So remember, an open unit ball, that would just be where I remove the boundary off each of my unit balls, like this, and like this. Okay, so it does not contain the boundary. Okay, and in general, we will actually not think just about balls centered at 0. We want to be able to think about balls centered at any point in any space. So if this here represents the coordinates in Rn, right? So for example, usually we would have x, y in R2, or just x in R, or x, y, z in R3. I labeled them x1 all the way up until xn because in general you may have many, many more coordinates than just 3. So we would run out of letters here, x, y, z, and then what comes next. So this represents the ball of radius r centered at A. And it's the exact same construction as we did here, except now we want to consider only open balls centered at A. And maybe I shouldn't call it A, I'll call it x1 all the way up until xn. That's really the point that we're centering our ball around. Okay. And now, using this construction, we can actually rephrase the basis for the topology on R and extend it to Rn. What we will do is that we will describe the basis for the topology on Rn as the set of open balls in Rn. So, in other words, you have your, for example, in 2D space, we have any point, right? And that is going to be our center. So here in R2, I can use x, y. And what we're saying is that every single open ball that you could think of, centered at this point, is going to be a basis element. Okay, so this guy's a basis element, so is this guy, right? That's a lot of basis elements, right? There's, for every single point on R2, I have infinitely many choices because I have infinitely many choices of radius for my open balls. Okay? So here's our revised openness test for Rn. This, notice, will actually work inside R. It's just now we're generalizing it to higher dimensions. So if we have a subset in Rn, what we need to do is we need to pick a point inside our subset, and we need to ask ourselves, can you construct an open n ball that contains x and lies entirely inside U? So let's do some examples. The first one that we're going to do is the closed half plane. So that is going to be the set of all points that are above the x-axis, and it also includes the x-axis as well. Okay? Is this set open? You'll notice that this is actually a sort of mild generalization of the half-closed interval that we discussed in the previous example. So actually, any point here, you can obviously construct an open ball. It's quite easy to do if you just pick a ball whose radius is no bigger than this distance r here. So let's just draw that. So for any point, you just have to figure out its y-coordinate, and that distance will tell you exactly what the maximum open ball you can construct is. And we don't even need the maximum one. The fact that such a ball exists for every single point here means that this set is appearing to be open. However, there's one problem. Again, if I were to pick points on the boundary of my set, let's say I pick point right here, right? Now try and construct an open ball. Any type of open ball that you construct will always contain points that are below this x-axis, and that's not good. Remember, we require our open n balls to not only contain the point, but they also have to lie entirely inside my set. Right? U, again, here is my entire upper half plane. However, we can modify this example slightly to get ourselves back an open set, and that is just by deleting the x-axis. Once we delete the x-axis, notice now that every point, well, once again, we can create an open ball. So I'll just draw it dotted for now, but we can't do the same thing that we did here because we're not allowed to choose points along the x-axis. So even if you take a point that's really, really, really close, right? If I were to zoom in on this, right, there's actually going to be a little bit of distance between it and the x-axis. And that little distance will allow you to create an open ball. I'll draw it open. And now that we have an open ball, we can confirm that our set is open. Okay. So in general, a set in Rn is going to be open if it doesn't contain any points on its boundary. So this was obvious here, and you can also see how it applies to our very first example, because in our first example, the half-closed interval contained one boundary point. It contained the 0 boundary point. So in general, we are able to very quickly describe whether sets are open as long as they don't contain their boundary. Now, this doesn't work usually for any topological space, but for what we are doing in this program, it will be a very useful intuition to have. So it's one that you should keep. Okay. So maybe one final example, and this one is a little tricky one, is to show that any open ball is open. Okay, now you may be laughing at this a little bit because it sounds like very stupid. I mean, didn't you already say it's an open ball? Well, no. Like I said at the beginning, the word open with topology doesn't actually mean anything until you've defined your topology. So we called these guys open balls, right? These balls here without their boundary, we called them open balls, but that doesn't actually mean they're open. It doesn't actually show that they are part of the topology. So to show that the open ball is open, what we can do is we can just, let's do it in R2 for now. We'll describe an open ball here. Let's do one that's centered at 0. Maybe for reference, we'll just pick the unit ball, okay? Now, this is an open ball, and what we can do is that for every point inside the open ball, let's pick a point here, we can take its distance, its minimum distance to the boundary. Let's call this distance r. And now what we can say about this r is that if I draw around my point x a little ball of radius r, well then that ball is going to fit entirely inside my big open ball. I'll call it like B1, 0 for now. Again, what this notation means is that the radius is 1 and the center is 0, 0. All right, but now that I've done this, I can generalize this argument to any point inside B1, 0, 0. And once I've done this, I've proven essentially that this thing here is open. And that's how you prove that open balls are open, right? It's not actually a trivial proof. It's not like a proof by definition. You actually have to show that for every point I pick, right, I can find an open ball that lies entirely inside B1, 0, 0. And of course, the open ball is going to have to be a bit smaller than B1, 0, 0. Okay. So this is generally how we test for openness in Rn. And I know this talk has gotten a little technical, so I'm going to promise that next live session, we are going to go through a multitude of examples that will tie in what we've seen together in the last 2 videos, and we'll actually be able to describe some more interesting invariants using this terminology here.